Hi, my name is Benedikt Mersch, and today I will show you how we can use mobile robots in dynamic environments and make them not only perceive the spatial but also the temporal aspects of it. First of all, I would like to motivate why we want to use mobile robots in general. And on this picture you see how they can transport us more efficiently. So here we have an autonomous vehicle that is able to transport people from A to B without the need of a human driver. And such a system, or such systems, can help us to reduce the number of cars in the city and therefore also reduce the number of traffic jams that we have. They can also make our roads more safe. So in this example we see a white bike memorial, which usually reminds us of a place where a tragic traffic accident took place. And using intelligent perception systems that mobile robots are equipped with, we can make the roads more safe because we are able to identify vulnerable road users a lot earlier and then either warn the driver or intervene. Mobile robots can also support us more sustainably. So in this example, the image, you see a robot that is operating in an orchard, and this system can, for example, analyze the growth of plants and then use less fertilizers or herbicides that we would normally use. All these platforms, all cases, have one thing in common. The robots have to operate in dynamic environments. And in the first two examples, this is quite clear because we have moving objects in the environment. But also the third one is actually dynamic because it contains structural changes. So the environment itself is changing over time. And all these can be challenges for a mobile system to take the right decisions because of moving or dynamic objects or changes. And let us first have a look at what sensors these robots can use in order to analyze what is happening around us. And on the left you see the IPV car that I was also supporting or developing during my PhD. So this platform, or perception platform, has multiple sensors. For example, a 3D LiDAR that gives us a precise 3D measurement of our surroundings, as you can see at the top right, but also cameras that give us additional color information, as you see in the image. We can also use other sensors like GNSS receivers, IMUs or radars, but today in this talk I will mostly focus on 3D LiDARs because they give us a precise 3D measurement and can also work under bad lighting conditions. Here we see what the autonomous car sees with the LiDAR. So we have our 3D point cloud and our planned path in red, and now over time, while the car is driving, we collect more and more of these LiDAR scans, and the color here indicates the different timestamps of the corresponding point cloud. At this point in time, we can now look at the last timestamps we received and start analyzing what we observe here. And for example, here we already have a moving bicyclist next to us and also a parked car. And the first question we can ask is, what is actually moving around us? This is very important to do further decisions, for example, to decide whether an object can collide with us or if we can use such a point to localize. So we're in general interested in which parts belong to moving objects and which parts belong to static parts. And with the static parts we can localize or build maps, and the moving parts we need to pay further attention later on in planning, for example. And one possible next question could then be, where is an object moving to? So after knowing which objects move, we can ask, what are they going to do in the future? So in this case we would like to know whether the bicyclist is just driving straight or is even taking a left turn and then interfering with our path, or the same with the car that we see in front of us. And these two questions are also the main questions I covered in my PhD thesis. So on the one hand, the what is moving question and the question of where is an object moving to. And among these, I contributed to 6 different works. The first 2 are about LiDAR-based moving object segmentation. The third one is a dataset that we can use to further analyze the efficiency of these models in new environments and with new sensors. The fourth is a system that is able to localize using stable points. And on the side of where is an object moving to question, I developed one work that is able to predict future trajectories in a supervised fashion. And the last work, the 6th one, that can predict future point clouds in a self-supervised way. And due to the time today, I will only focus on the left part, so about the what is moving question, and more specifically, I will present the 2 works on moving object segmentation and also the last one about the stable localization. Let us directly start with the first topic, and I would first clarify what the task of moving object segmentation really is. Here we see again our example from before, where we have our past point clouds that we measured, in this case 5, and we see the parked car and the bicyclist. Again, the blue color indicates the different timestamps the scan was taken, and the goal is now, given this as input, to decide for each point if it belongs to a moving object or not. So in this case, we colorize the moving objects in red, so the bicyclist, and the remaining points, so the ground and the parked car, as non-moving, and they are colored in black. So this is the goal or the desired output of the method. Let us first take a step back and have a look at how other approaches did this in the past. So in general, you could also use a point cloud segmentation method, so a semantic point cloud segmentation method, which assigns a semantic label for each point. So of course, you would also need to use multiple scans for this, and then you can assign or determine a semantic label, for example, say this is a parked car, this is a moving car, or a pole or street and building. And then you could say that buildings are of course non-moving, streets as well, whereas moving cars belong to those objects that we need to pay further attention to. The drawback of such an approach is that they need all these semantic class labels for training, and we also do not know if the objects that we now encounter have been part of the training data. So if there's, for example, a moving object next to us for which the semantic class is not known because the model has never seen such an object during training, for example, a baby stroller or a person with a cart, it is not clear if it's able to segment this object properly, and we cannot guarantee that this is a moving object which is being detected. This is why we then focused, or the community focused, on not segmenting semantic objects, but in general moving objects, so only doing a binary classification. Among these, we have methods that work on range images. So in this case, the range image is basically the natural representation of a rotating LiDAR scanner, which shoots beams in a column and then shifts this column forward, resulting in an image structure in which each pixel corresponds to the range measurement of a corresponding ray. And the first methods that did moving object segmentation used such a range image and then segmented the image into moving pixels or moving points in red and non-moving points or pixels in black. And the advantage here is that you can use 2D image-based techniques to do that. However, there's also a drawback for these methods, which is that they usually overfit to the dimensions of the range image, or in general the nature of the range image. So because they're often learning based, so they use training data to do the segmentation, they often cannot generalize to new sensors, because either these sensors have different range images, or the range images look differently, or they cannot even deliver a range image because it's not a rotating LiDAR scanner. The other problem these methods often have is that the label bleeding occurs. So if you segment the image or the scan in this range image, here you see, for example, two moving objects that are very close in the range image. This does not often correspond to a correct segmentation in the 3D world. So if we go back from the 2D range image to the 3D representation to the points, we can see that these cars or objects were close in the range image, but they're actually further apart in the 3D world. And in this case, we call this label bleeding because the labels of the moving object in the front were bleeding into the object in the background. In this case, because they were semantically close, so both were cars, so it was maybe not easy in the range image to distinguish where the one car ends and the other one starts. And also sometimes they miss parts of a car because they do not use the 3D information fully. So our proposed approach, so this new approach, is able to segment moving objects without caring about the semantic class, and we do it directly in 4D, so we do not need this projection to a 2D image. And this approach we call 4DMOS, and I will now guide you step by step through the individual steps. On the left, we have a sequence of past point clouds, and we look at a limited sequence, so a limited window of those scans. We transform all scans into a common reference frame using odometry, for example with KISS-ICP, and then we attach a timestamp to each point that tells us the time of the corresponding scan. So in this case we have a 4D point cloud, so X, Y, Z and time, and we can further process it. This is the point that I already showed you before. So in this case, again, the color indicates the timestamp. And one drawback we now see is that this is a lot of data to process, especially with modern LiDAR scanners. If we now process each point individually, this is not really doable online. So what we do is we go from a point representation to a pixel or to a voxel representation. So basically a generalized version of pixels. We do this by voxelizing our space. So in this case, the 4D space. So we have a voxel index for X, Y, and Z coordinates, but also for the time. And then just take the information which voxel is occupied at a specific location and timestamp. We then see that a lot of voxels are actually empty because we did not measure any points in here, and we decide to only keep the occupied voxels in order to obtain a more memory and computationally efficient representation. So we throw away these empty voxels and only keep those occupied ones. And the intuition now is that we want to automatically extract the information of moving objects, or in this case moving voxels, based on how their occupancy changes over time. So here we see that those occupied voxels for the parked car on the left are all at the same location more or less over time, whereas the occupancy of that bicycle changes the location over time. So the goal is to then segment this voxel grid into moving and non-moving voxels, and based basically on this movement over time. And this we do by using a sparse convolutional neural network, so basically a generalized convolutional neural network that is working on 4D data and also on sparse tensors in this case. So we do not need to do convolutions along those empty voxels. This is the main advantage. And we do this using an off-the-shelf CNN, so an off-the-shelf sparse 4D CNN. So this one has an encoder-decoder structure, so it first compresses and encodes the features into a smaller dimensional representation and then decodes again to the original resolution. And then, since we know for each point in which voxel it fell, we can go back from a voxel prediction of moving and non-moving to the individual points. And then based on the timestamp, we can get back to the original scan segmentation. Of course, we need to optimize the weights of this network, and this we then do by comparing our predicted segmentation with a ground truth segmentation, so a labeled data set. And we can then optimize the weights in a way that these are as close as possible. And if we now look at the results, so here we trained our approach on the semantic kitty dataset, which is a public benchmark for semantic but also moving object segmentation. And this now is seen from the validation data. So this scene was not seen during training, and we can see that our approach is able to successfully segment the moving objects, so the cyclist next to us, but also the moving car at the top, to be moving, and the remaining parts or points to be non-moving. If we go back to the example with the ladle bleeding, we can also see that since we now directly decide whether it's moving or non-moving in the 4D space, so without this projection, we can easily distinguish different objects or instances, like in this case, the car in front, which is moving, and the car in back, which is parked. So there's no more ladle bleeding, and in general, a better segmentation. We also compared our approach to multiple benchmarks on the MOS benchmark. To multiple baselines on the MOS benchmark. The metric we report here is the intersection over union of the moving points. So we take the number of true positives of our prediction or classification divided by the number of true positives plus two types of errors that we could do. So false positives, points that we believe are moving, but they're actually not, and false negatives, points that are actually moving, but we believe they're static. So ideally this number is close to 1 or 100%. So the higher the better. And here you see two baselines that do a multi-scan semantic segmentation and two methods that operate based on range images. And we can see that our approach is on par or better than these. The question is, can we do even better? And so after developing 4D MOS, we saw that sometimes it's not easy to identify the motion, especially for slowly moving objects, since we only consider a limited number of scans. So the more scans we use for the segmentation, the better the result usually, but also the slower the runtime, because we need to do the convolutions over all these timestamps. And if we look at this example, we have this moving cyclist, and now there's a tree in front, and if we now only look at those 5 scans, it is not easy to identify this object to be moving. The other problem can be that, or another thing we don't really exploit yet, is that if we know, for example, that behind that tree we already observed a moving object in the past, if now we again measure points, we should know that this is also a moving object, because moving objects usually occupy the same space, so the space which is free, whereas static objects, of course, stay at where they are because they are static. So we do not use any knowledge about where we have seen moving objects before. This is the second drawback or thing that we can improve, and that is why the next approach I will present does not use the sequence of scans, but a local map. And this local map contains all past information that we have about an environment, about previous measurements. And at the same time, we maintain a volumetric belief that tells us where we have seen moving objects before already. This approach is called MapMOS, and this is the overall architecture. So in the middle you can again see our 4D CNN from before, but now the input looks different. So we have, instead of a sequence of scans, now our current scan and the local map. So this local map is the same map we use for odometry. It's basically a collection of past point clouds in a downsampled fashion. And we again register the scan with this map and then attach a timestamp, either a scan timestamp or a map timestamp, depending on from where it was coming. And we do the same voxelization as before. At the output stage, we again get a per point prediction, this time for basically all points in the scan and also the map. And as you see in this image, we can now distinguish or identify also these ghost trails, so the points of moving objects that we still have in our local map. You might now ask, what is the advantage of such a local map? So in this example here, we have a current scan in blue, so the current LiDAR scan, and our local map in black. And here we have a slowly walking pedestrian, and at time t, our method is not able to identify this pedestrian to be moving because it just started moving, so there's not much motion visible. If we now wait for 1 second more and we observe more points of that pedestrian, and since it's moving, we will observe these points at different locations, at some point our approach manages to identify the motion and then successfully label both the pedestrian in the current scan, but also the points in the map to be moving. And this is because we gathered more information about the object. The remaining question now is, if we do this online, so we get all these predictions at each timestamp, how can we fuse these different predictions which are even contradicting? And for this we developed a dynamic environment model. So we again voxelize our space, maybe at a different resolution, that depends on how fine-grained you want to have this model. And each voxel now has a dynamic occupancy state, MI. And this state tells us, as you can see below, that a voxel is either occupied by static objects, so the voxel itself is static, or the voxel can be occupied by moving objects. So this does not mean that there is a moving object in the voxel right now, it just means that this is a part of the space in which we have observed a moving object. So if ever again we observe a point in here, this must also come from a moving object. And again, the intuition is that moving objects move in the same space, whereas static objects just stay where they are. And the goal is now to take all these measurements that we have and get predictions for the scan and map, and then estimate the state using a binary Bayes filter. This static state binary Bayes filter is a very efficient way to estimate the state of each voxel. And the way we do it is, at the bottom you see our current volumetric belief, so all the voxels with the current belief of either being moving or static. And at the top we have the current segmentation of the scan and the local map. So blue is the current scan points that we believe are static, black are the current map points that we believe are static, and in red we see the points that we believe are moving. And with this efficient filter update, we can now update each voxel belief below by basically just indexing the corresponding voxel a point belongs to, and then fusing these scores that we estimate with our sparse 4D CNN. And the idea is that basically those moving predictions contribute to a voxel belief to be towards moving or dynamically occupied, and static points contribute to a voxel's belief to be a static voxel. And the nice effect about this filter is that it automatically filters out false positives as shown here. So here the belief of the voxel is already very certain to be static. So if you now have this moving points on the ground, for example, and you integrate these, the belief of the corresponding voxel in the ground will not change much, because the belief is already very certain to be static. So if you just observe or think to observe a moving object once, it does not change the final belief. So we can more robustly filter out these false positives. And at the same time, if there's a region, like a voxel in which we observed moving objects before, even if our current segmentation did not catch this moving object, if we know that this is a space in which we observe moving objects, we can recover this. So we can also recover false negatives here. This is now the final step of MapMoS on the right. So we do this belief update that gives us an updated volumetric belief, and then we can use for example, the point cloud from the scan, or also any other point that you want to know the current state of, and you can index the corresponding voxel and then get the final belief. We tested our approach in a mapping scenario in which we compare first building a map just integrating all points, so without any filtering. And you can see this is a very busy sequence from kiddie tracking in which a lot of pedestrians walk around. So if we build a map from this using all points, we will have all these traces of moving objects in the map. If we then use 4D-MOS, we can use 4D-MOS to segment the scan into moving and non-moving, and then only integrate the non-moving parts into the map. We can already filter out most moving objects, but some are still there. And if we now use MapMoS, so we use our volumetric belief and fuse our scan and map segmentation into the belief, and then wait for 1 second, and then ask the corresponding belief map which points are static and which are moving, we can clean the scan or map even more, and in this case generate this map also online, by the way, which is almost completely cleared of moving objects. There are just a few artifacts left, but this map is now well usable for planning and navigation. We also tested our approach on some data that we recorded with our IPB car. So here the method was trained on semantic kitty, so the dataset that I mentioned before. And without further retraining, we tested how well it generalizes to a new environment and a new sensor. And in this video, you see, for reference, the camera image below. It's a very busy sequence with a lot of pedestrians. Actually happened in Altstadt during the cherry blossoms. So a lot of people go visiting in Bonn and check out the nicely looking trees. And we of course have to drive slowly here because of moving objects. But our approach successfully segments most of these objects to be moving, as you can see by the red color. We further followed this generalization capability, or the investigation of this, and compared different approaches on different variations of, let's say, domain shift. So here the top two methods are again range image based approaches, and below you see our 4D-MOS and MapMoS in comparison. And the first column shows the result of kiddie tracking, which is the sequence I showed during the mapping experiment. So it's using the same sensor, the same car for recording, but in a different environment. And our approaches already work better than the range image based ones. The next column, Apollo, now has the same sensor model, but mounted on a different car and also recorded in a different city. And here the range image based methods already work a lot worse, because the dimension or the properties of the range images change. And since they have been trained on a specific type of range images or different, let's say, specifically looking range images, they cannot generalize to this new environment and new, for example, mounting height. So the height of the sensor changes on the car if you use a different car. And if you, for example, before kind of learned that moving objects are always in the center at a specific height because that's where the street is in your range image, then this will not work when you change the position of the sensor. And the rightmost column is now new scenes. So here we use even like a different sensor model. And for this one, we cannot even use the methods without retraining than the range image-based methods because they are trained on a completely different range image regarding the dimensions. If we now compare our approaches, they still work nicely and can also work with different sensors, as I have said. If you now compare the last two rows, you can also see that using our belief to further integrate measurements and then query the belief, we can always improve compared to the scan-based approach. Another interesting finding is that in the new scenes case, 4D MOS works even better, and this is because this sequence is very challenging for the odometry because it uses a sparser sensor, and since 4D MOS only looks at 5 scans, it mostly cares about local consistency of the odometry, so to align those 5 scans, whereas in MapMOS, if you have a few wrong alignments, your local map usually degrades, and this makes it very hard to then get a proper segmentation. So this shows a bit the sensitivity to the different, to the odometry. So you need a good pose estimation to estimate moving objects, especially for MapMOS. So to summarize the first part, I showed that we are now able to segment moving objects precisely in the 4D space without using any projection as opposed to prior methods. We developed a volumetric belief that allows us to re-estimate moving objects and also to fuse those in an efficient way to improve our robustness. And our approaches are able to generalize to new environments and sensors, which makes it more easy to deploy them on, for example, your datasets or your robots. So lastly, I would like to also talk about this last chapter of the first main research question, and this is about localizing using stable points. In this case, we go back to the example with the orchard robot or the vineyard robot. And these robots often operate autonomously in the vineyard and they require a reliable localization. So they're often equipped with LiDAR sensors, and especially in vineyards where, for example, the GPS reception is bad, or maybe if you operate under some trees, you want to use the LiDAR to localize in a prior map. So the way this usually works is that the robot is going around, for example, in April, where the plants are not grown yet. It maps the environment. This global map can be further refined by humans, can also be annotated. You can plan some missions in that map. And then later on in June, when, for example, the grapes grew or have grown, you want to use that scan from June and localize that scan in this map from before. This is actually quite challenging because we have moving objects in the scene, for example, from other workers, but we also have, and this is even more challenging, a changed environment. So if you look at a point that you measure on a plant in June, you will not be able to find the correspondence in the map from April because the plant was not grown yet. Whereas for other parts, like static parts, like this metal pole, for example, if you measure a point here, you can find the corresponding surface, or at least the close point in your global map. So this we call in general stable and unstable points. So stable points are, as I said, those points on the metal, for example, whereas unstable points are points without correspondence. So these could be points from moving objects, but also those from a changed environment. And what we now propose is an approach that is able to not only segment moving objects, but in general stable objects, using, again, our sparse 4D CNN, and doing this between our current scan from June and the global map from April. This is the overall architecture. You again see our sparse 4D CNN in the middle, and on the input side we use, similar to MapMOS, a scan and the map, but now basically the map from April, which can be human refined, as I said, and the current scan. We again do a voxelization, and in this case we add one additional module, which is pruning or removing voxels from the map which are not close to a scan voxel, and this is just because this map can be arbitrarily large and we of course need to somehow manage the size of it. We then use the same network, as I said. Of course we have to retrain again, and then get a per point segmentation. And this is now the segmentation of stable points and unstable points, and then we only forward those stable points to our localizer. And in this example, on this work, we use the normal distribution transform to localize, which then gives us the corresponding pose of the robot or the scan in the map. As I said, we need to retrain the approach, so we need labels for stable points, and for this we use a prior work, which is getting these labels from different runs in an environment. let's have a look at some qualitative results. So on the left you see again the robot operating in April, and on the right in June. So you have a different growth stage of the plants. In general here you see in gray the corresponding global map that we got in a prior month, and in black the stable points, in red the unstable points, and in yellow the submap voxels that we considered. In April there's not much vegetation, so we only have moving objects which we can now filter out after training our approach. And on the right you see that after those plants grew we can also segment these out, because as I said they will not have a correspondence in the map. So we are now able with our approach to filter out this changed environment. Here we see some quantitative localization results. So we here use the map from April and localize at a later point in time. So again with a lot of plants in the environment, and we show the cumulative probability to stay within a specific translational localization error. So ideally we want to be at 0 meter error in localization 100% of the time. So the more the curves go to the top left, the better. And first we can see a baseline in green LTSNet, which is filtering out stable points based on their appearance. But since this was trained on data up to June, it is not able to generalize to how unstable points, so how the plants look like in July. So in this case the result is even a bit worse than just using the raw data in blue, where we do not filter anything. And our approach in black, since it can filter out these unstable points, it improves the overall localization result. So to summarize the second part of this talk about my thesis, we can say that we are now able to not only segment moving objects but also environmental changes, and we can show that the localization using those stable points is more reliable and more robust in those environments. So to summarize, in my PhD thesis, I contributed to several methods that use sparse convolutions for spatial-temporal perception tasks. All these approaches, or most of them, they are able to generalize to new environments and sensors, so it should be easy to use them on new data sets or with other robots. And I've shown throughout the thesis that we can use these methods to, for example, improve the static mapping of an environment by removing moving objects, or also to improve the long-term localization, for example, in a vineyard. And overall, in the thesis, I covered the questions of what is moving in a scene, and also where is an object moving to in the future, although of course today we only covered the first question. Overall in my PhD, I contributed to 3 journal papers, 2 conference papers, 14 collaborations with my colleagues, and we got 1 paper award for KISS ICP. I also always try to, or push to, open source the code for my projects, so you can find most of them on GitHub, and I still try to actively maintain them. So if you want to check out what we did, just have a look at the website or our GitHub, and you can try out most of the projects by yourself. So to summarize again, these are my contributions, and thanks for your attention.